In Bell work today, we're continuing what we did yesterday with terms of optimization. This problem should look pretty similar to yesterday. Okay, just a warning on these problems. Optimization is not crazy difficult, but there are lots of steps and there's places you could make a mistake. In terms of like importance level of things that we're doing, okay, compared to the AP exam, optimization is great. It is not a big chunk of the AP exam. Okay, mean value theorem is much more important. I guarantee that's going to be on there multiple times. Okay, linearization is more important on the AP exam. L'Hopital's rule is way more important on the AP exam. Optimization in this capacity is not to the same level. Okay, so if you get done with today and you're like, yeah, I'm not great at that yet, it's okay. It's not as big of a chunk. Okay, we're going to get better with it, but it's not as big of a chunk of what we need. Okay, so with that in mind, let's go to work here. Find two non negative numbers whose sum is 9 and that the product of one number and the square of the other number is a maximum. Okay, I put that in parentheses because otherwise kids were reading that incorrectly. All right, so we look at this problem. We can tell it's an optimization question because I'm trying to maximize or minimize something. What am I trying to maximize here? The product. We are trying to find the maximum product. All right, so we're going to start off by writing a product equation. Okay, so the product of one number. So what do we want to call that one number? X. And the square of the other number. So what do we want to call the other number? Y squared. It's product, so we're multiplying them together. That is my product equation. X times y squared. What is the problem with that equation right here? Two variables, so we need another one. So Max Harris, what's your other equation going to look like? The sum is 9. So if the sum is 9, x plus y equals 9. So we're going to use this secondary equation to help us on the other one. Okay, so if we're doing that here, Taylin, what letter did you solve for? Great, she solved for x, so that's what we're going to go with. So it's 9 minus y. She just moved this y to the other side. What'd you do once you've solved for a letter? You plug it in. She's taking this and she's plugging it in for x. I appreciate that she solved for x because otherwise we'd have to FOIL and nobody wants to do that. Okay, so good. So my product equation now is going to be 9 minus y times y squared. You could technically take the derivative at this point, but you have to use product rule. So don't distribute first because then you don't have to do product rule. So my product is going to be 9y squared minus y cubed. That is a derivative, or that is the equation I'm trying to maximize. It's in terms of one variable. That's what I want it to be. Okay, so we have our product equation. It's in one variable. Once I've gotten to this point, Michael, what should I do next? We want to maximize this. So if I want to maximize that, what do I got to do? I got to take the derivative and set it equal to 0, right? Take the derivative here. So p prime. So if I'm taking p prime here, Macy, what's my derivative going to look like? You're good. You, yeah, and there's a lot of different ways you could have written that. There's nothing wrong with any of them. This is what I'm doing, so your paper might look slightly different. I took the derivative. I set it equal to 0. Well, what can I factor out here? Negative 3y, sure. I'm going to leave the negative in there. But yes, we could take the 3y. You could take the negative out as well. I'm just being lazy. If I take 3y out of this, I'm left with 6. If I take 3y out of that, I'm left with minus y. We're taking each thing and setting it equal to 0. So y equals 0 and 6, because 6 minus 6 gets me 0. Again, you probably can make a decision from this point what you think the maximum is going to be. Okay, but let's throw it on a number line just to check. This is a p prime number line. We make number lines of derivatives. Okay. Notice here that they said non-negative. So if it's non-negative, what's the smallest number I can plug in here? 0 is the smallest. There is going to be a maximum here. What is the biggest number I could possibly plug in? 9, because the sum is 9. If you don't plug anything less than 0, then the biggest number you could possibly plug in is 9. Yes, sir. No, this is a quadratic. I've got a y squared and a y, so if I have a y squared and a y, I've got a factor. You cannot just solve there. It doesn't work that way. Yeah, but it's not, it's on accident. Yep. And so I got 0 and 6. I'm plugging in numbers. Pick a number between 0 and 6. 1, we are plugging it into the derivative. So if I plug in 1 here, this would be positive, that would be positive, so this is positive. Picking a number between 6 and 9. Let's go with like 8, 18. Yeah, that's going to be negative. We already pretty much assumed that 6 was going to be the maximum, but that just proves our point that P prime is positive, so I'm increasing, and then it's negative, so I'm decreasing. That makes 6 the max, 0 the min, and 9 the min, which would make sense because if my two numbers were 0 and 9, my product would be 0. That's as small as I can get. So we think 6 is the maximum. We're finding two non-negative numbers. So we know that y is 6. That's what we've decided. If y is 6, what's my x going to be? 3, because it's got to be x plus y equals 9. So if one's 6, the other one's got to be 3. Questions there? Great. All right, so we're finishing example 3 from yesterday. We did part of it in class. Let's do the other one. All right, we drew a box. I don't know if I have this on video already, so I'm going to quickly go through this. You have a square base and a surface area of 108 square inches. Okay, so the square base is x and x. The surface area is 108. We are trying to maximize the volume. So if I want to maximize this volume, it's x times y, or x squared y. That's my volume. My surface area is 108, and it's going to be equal to x squared, this base. And then I'm going to have 4 panels on this box, like this panel right here, that are x times y. Okay, so that gave me this problem. I'm going to get y by itself. So I subtracted x squared. Then I'm going to divide by 4x, divide by 4x. 108 over 4x minus x squared over x, over 4x is going to be equal to y. I'm simplifying here. 108 over 4 is 27 over x. And that thing right there, x squared over 4x, is going to get me x over 4. And that is going to be all equal to 4. I'm not 4. That's a y. I'm an idiot. All right. Everybody okay to this point? We are substituting in. We are taking this guy right here, and I am plugging it in for y. So my new velocity, or my new volume equation, x squared times 27 over x minus x over 4. That's volume. What am I going to do with volume in order to maximize it? Take the derivative. So I need to take that derivative. Again, I don't want to leave it like this. If I did it right now, I'd have to use product rule. I want to avoid that. Okay, so I'm going to try to clean this up. So I'm going to multiply both things by x squared. So x squared times 27 over x. What am I going to get if I take x squared times 27 over x? 27x, because one of those x's is going to cancel. Okay? Then I got this other one. All right. 27x. And then I'm taking x squared. So it's going to be minus x squared times x would be x cubed. And if you want to make yourself feel better, write it as 1/4 x cubed. That's my volume. What do I need to do with that thing next? Take the derivative. Go ahead and do that. Take the derivative real quick with your neighbor. Go. We're taking the derivative. Luke, what's the derivative going to be? 3/4 x squared. That's his derivative. Once we take that derivative, what are we going to do with it? Set it equal to 0. So 27 minus 3/4 x squared equals 0. It looks kind of funky. Okay? You can solve that. We can solve it. It's not a It's got a quadratic term, but it doesn't have a linear term, so I don't have to factor. I can just simply solve. Andrew, what'd you do at this point to solve? Yep. So we'll move the 27 to the other side, negative 27. Then what? Yeah, divide by negative 3/4, or in other words, multiply by negative 4/3 on both sides. That's going to cancel. I get x squared equals, it's going to be positive. It is 36, because 27 divided by 3 is 9, and then 9 times 4 is 36. So if x squared is 36, what do you think x is going to be? It is technically plus or minus 6. We're dealing with a box. Do you think that if we're dealing with a box, we want to have a negative side? No. The answer is going to be a positive 6. Okay. If we want to be good math students, okay, we would throw this on a number line. Now, for these problems, it's not crazy important. Okay. We will get to problems where we have to do a chart, and that's going to be, again, more second semester. Okay. But we could go 0. We could go 6. If I plug in a number, again, I'm plugging it into the derivative. Okay, I'm plugging it in right there. If I plug in a number like 1, it's going to be positive. If I plug in a number like 8, it's going to be negative. If I change from positive to negative, is x going to be 6? Or I'm sorry, is that going to be a maximum? That's a max. And so what we figured out is x is going to be 6. But the question is, what are the dimensions of this box? So I know x is 6. I know the other side is going to be 6 because it's a square base. I've still got to find the y. What am I going to do to solve for y? Plug it into what? Surface area equation, because this gives me an equation here. So 6 squared is 36, and then I would divide by 24. Y is going to get you 3. Just plug it in. I'm not spending a lot of time doing that because I know you can. Yes, ma'am. There would absolutely be a limit in terms of what it would be. Again, it's not a number that's going to matter to us here. It's definitely can't be bigger than I don't even know where you would start with that. It's one of those things that it's not going to matter in terms of what's going on, but you're correct. There would be some sort of limiting factor here. It's a good question. Everybody else good there? All right, let's go to example 4. So example 4, this is a question that we would have done back in pre-calc. Maybe not this exact level, but we did these farmer questions before. Okay, I could take you to my pre-calc notes from earlier this year, and we did these problems in class. But let's look at it. A farmer wants to fence in 180,000 square feet of land in a rectangular plot, and then divide it into 3 equal parts. Okay, so imagine what's going on here. This is his land. It's rectangular. He's going to divide it into 3 equal parts. So he's going to have this shape right here. We've got 1, 2, 3 equal parts. What is the least amount of fence needed to accomplish this? So again, I know it's a maximization, or I'm sorry, an optimization question, because I see that we're trying to optimize the situation. What is the ultimate goal on this problem? To get a minimum. Good. I want to have minimum fence. Okay, so we're going to write a fencing equation. Fence is going to be equal to what here? Work with your neighbor. Try to come up with an equation for the fencing of that box. So somebody have a good equation here for your fence. 2x plus 4y. Somebody have something, we have some stuff similar to that? Could have flipped your x and your y. Anybody have 6x plus 4y or 6y plus 4x? That works as well. Okay, here's the idea. This is one side. She called it x. Here is her other side. She called that x. And then we had 1, 2, 3, 4 separating things. She called that y. You could have had something similar and different, and in the end, you would get the same answer. Okay, you could have had something different. This is what I'm going to go with. So if you want to follow along with me, I'd suggest you adjust. That's my fence equation. I want to minimize that because I'm trying to do the least amount. What's the problem with that right now? There's 2 variables. There's an x and a y. Write your other equation that's going to help us out here. Go. Anybody confident in her second equation here? Max, what do you think? Yep, good. 180,000 equals x times y because it's 180,000 square feet of land. It's rectangular, so it's base times height. His base is x, his height is y. 180,000 equals xy. That's what we got. What do I need to do with this thing in order to help me with the fence equation? Substitute, get something by itself. What do we want to get by itself? X, great. Let's get x by itself. So if I get x by itself, I'm going to divide by y. So that means I'm taking this thing right here and I'm going to substitute it for x because that's what x is equal to. So I'm putting it right there. So let's do that. Fence is equal to 2 times 180,000 over y plus 4y. Or in other words, fence is equal to 360,000. Instead of writing over y, since I'm getting ready to take a derivative, what else could I write? Y to the negative 1 plus 4y. That is my fencing equation. Then I'm going to take the derivative, set it equal to 0, and solve. Go. We need to take the derivative. We need to find f prime. So if I'm finding f prime here, Emma, what'd you get for f prime? Good. Plus 4, and she's going to set that thing equal to 0. Great. That's f prime. We're setting it equal to 0. Okay. This looks weird. It's not as bad as it seems. Okay. If I want to solve for y, let's move the 4 to the other side. So it's going to be equals negative 4. I'm sorry, I forgot my y to the negative 2. Okay, so I just moved that over. I want to solve that. Okay, so what could I do with that negative? Or let's do this. I don't like y to the negative 2. That looks funky. We're not used to solving that. What could I write instead of y to the negative 2? Divided by y squared. I don't want to solve it with the y squared on the bottom. How would I get rid of the y squared? Multiply both sides by y squared. So basically, that y to the negative 2, oh, that really just means I need to move it to the other side. So then I get this problem. Negative 360,000 equals negative 4y squared. Now it looks a little more normal. It looked really strange there for a second. Divide by negative 4. Divide by negative 4. I get y squared equals 90,000. Square root. Square root. What's y going to be equal to? Plus or minus 300. The square root of 90,000 is 300. Again, we're going to use our brains and assume that we've got the right answer. But let's throw it on a sign chart just to make sure. The smallest fence I can have is 0. Okay, I don't really care what the other number is, but we can put 300 on here. We are plugging into the derivative. So if I plugged in 1 into this derivative, it's going to get me negative. If I plugged in a number bigger than 300, it's going to get me positive. Does that make 300 a minimum? Yeah, f prime changed from negative to positive. That's just a good check. Oh, yeah, it's a minimum. Okay, that means my y is going to be 300. How could I figure out my x? Plug it in. I plug it into my area equation right here, right? Because I can do that if I plug in right there. I would just plug it in and go. X is 600. Is that the answer to this question? I need the least amount of fence, so I would still need to go back and plug in. Now that I know that X is 600 and I know that my Y is 300, I could go ahead and finish that problem. And so I trust you to be able to do that, but my missing fence, or my fence that I need here, is 2,400 feet. This is not a question that they would necessarily ask as a free response, but sure. Questions on 4? Again, optimization. They're great questions. Okay. They are a little bit more complicated. We did quite a bit of work for one question. That's not normally the calculus way that you got to do this much work for a single question. It is not a free response question. I've never seen one like this as free response. They could be multiple choice, but if they are multiple choice, they would look like this one. Okay, so this is a good representation of a multiple choice question. The points 3, 0, x, 0, x, comma 1 over x squared, and 3, comma 1 over x squared are the vertices of a rectangle, where x is bigger than 3. For what x does the rectangle have a maximum area? We are trying to maximize area. So when I read that, I'm thinking, all right, this is an optimization equation. I'm trying to maximize area. Understand what they're doing here, okay? Basically, they're saying this point right here doesn't change. But we're going to draw different rectangles that go to this line. So it could look like that. Or maybe it looks like that. Okay, you could have different ones. We are trying to optimize the area. Use your brain here. Think about this rectangle that is drawn. What is the equation of the area going to be? Come up with that. Base times height, it's area of a rectangle. Think about what could it be just in terms of x. Go. Anybody got a good equation for us here for area? Luke, what you got for us? Times 1 over x squared. It's a great answer. Okay. X minus 3. That's going to be the base of this box because it's whatever your x value is, but it's not the whole x because I'm going to stop it at 3. So x minus 3 is 1, and then the y value is going to be that thing right there. That's always going to be the y value. It just is dependent on the x. That's my area equation. Oh, good. It's in terms of one variable. That's a good thing. Okay. We're going to have to take the derivative of it. And so instead of leaving it like this, and let's go ahead and distribute. Okay, because if we distribute that thing, it'll help us out. 1 over x squared times x. That would get me 1 over x, or maybe even better, x to the negative 1. 1 over x squared times negative 3 is going to get me negative 3 over x squared, or maybe better, negative 3x to the negative 2. Again, I'd rather write it with a negative exponent because my next step is to take a derivative. Do that now. Okay, that is your area equation. Take the derivative, set it equal to 0, and solve it. When you get an answer, show it to me so I can see how you did. A prime, we're taking the derivative. So, Jacob, what's my derivative going to look like here? Good. And then what's my other one going to be? Good. Good. That's his derivative. He's taking that thing and setting it equal to 0. Even though this is strange, we can do a little work here. Cannon, what could I do to solve this thing? Yeah, so we're going to take out an x to the negative 2. If I took that out of this first one, it would leave me with negative 1. If I took it out of the other one, it would leave me with 6x to the negative 1. And instead of 6x to the negative 1, I'm going to write that as 6 over x. Okay, just be fluid and be able to move back and forth. I want to know when this is equal to 0. X to the negative 2 equals 0. Do we really care about that answer? Because it can't be 0. We said that x has to be greater than or equal to 3. And so that doesn't fit because it's got to be 3. So it's not that one. So that means I'm just solving this. If it's 6 over x equals 1, because I would just take that 1 over, what does x need to be? 6. And you could plug in some numbers, but you will find out that it will go from positive to negative there. That makes 6 a maximum. Again, optimization is difficult. It is not the number one most important thing in this chapter. Even though it's the one we're going to spend the most time on because it's the most difficult, I would say it's probably the least important thing in this chapter in terms of like how much it's going to show up on the AP exam. So I want you to know it. We're going to be good at it. But at the same time, as we get to April or we get to May, it's not going to be something we spend quite as much time on as other things. Work assignment.